Alright, number one, we're given the population of a certain inner city area is estimated to be declining according to this model. So we're given P of T is equal to 335,000, and then it's E raised to the negative 0.023P. And it says where T is the number of years from the present. What does this model predict will be in 13 years, around to the nearest person? So all we're going to do is number crunch. We're going to put this in our calculator and find its value. So we don't even really need to do anything other than that. But we want 13 years. T is the number of years. So I'm going to plug this in and plug a 13 for T. I'm going to clear out what I have. 335, 0, 0, 0. Now, on the left side of the calculator, LN, above it in blue is E to the X. If you hit the second and then the LN button, you get that E waiting on the input. We're going to input negative 0.023. So I don't need the 0 in front of the decimal. It doesn't make a difference, but I do need the one after. And then it's waiting on the input T. I'm just going to put in parentheses because T, we're told, is 13. So that's going to multiply times 13. So that's exactly what we need. You hit enter, and we're given this number, and we want to round to the nearest whole number, the nearest person. So 248,422. 248,422. Alright, and then question number 2, there are 2 parts. A certain species of alligators is introduced into a swamp, and wildlife experts estimate the population will grow to TT 988 times 4 to the T divided by 3 power, where T represents the number of years from time of induction. So these alligators are going to be growing in this wildlife, and we want to know what is the quadrupling time for alligators. So what I'm going to do this time is I'm going to go to y equal, and I'm going to put that formula into y equal. So the PT is just going to represent my y, and I'm going to do in parentheses 998 close, and then 4, and then raise it to T divided by 3. The calculator variable input is X. I'm going to do X divided by 3. Alright, and then I'm going to do second graph. So we want to know when this is quadrupling. So I'm going to go to, I guess I can just hold the arrow up and go all the way back to 1. You can do table set if I do second window, and I can just enter 1, so it starts me back at 1. And I go back to second graph to do the table. So I want to know when this is going to quadruple. So 998, if that times 4, that's almost 4,000. So one of these numbers should be close to 4,000. Looks like this one, 3992. So let's go back and make sure. So that would be 3 years. Second quit. I'm going to do 998 times 4. Why am I doing times 4? Because we want to know quadrupling. Quadruple means 4 times. So we're going to multiply the starting amount times 4. So according to that formula, that's going to be 3992. And then if we go back second graph to see our table, that 3992 number happened in 3 years. So it's going to take 3 years for these alligators to quadruple in size. So my answer is 3. And then part 2 wants to know how long will it take for the population to reach 15,968. So this is just according to the model. So if I just continue going down this list, 15,968, that happens in 6 years. So here we don't have to do a lot, we just let the calculator work for us. You can do this by hand, but I'm showing you with technology. So that happens in 6 years. Now, if you were to try to work this by hand, what you would do, let me just kind of show you that part, and then I'll give you the setup, and then I'll let you plug it in a calculator and you can verify it. So we want to know how long would it take to get to the 15,968. So first I would write down the formula. So this is representing the number of alligators at any given time, knowing the number of years that have passed. We got 998, and then there's 4, and then T over 3. Okay, so you're going to replace this with the final value, which is the 15,968. 8 equals, and then this one, 998, 4, and then T divided by 3. Alright, so you're going to divide by the 998 on both sides. Divide by 998. That will divide out, leaving us with whatever this is. I'm not going to actually do it yet, but I'm going to write down the formula. So you can actually divide that. I like to leave it whole numbers because I don't know if it's going to come out to be a decimal or not. Equal to 4T over 3. Now, you need to understand rewriting this. If you have a fractional exponent, the bottom number is the radical, the top number is the power. So what this means, just this part right here, it means the cube root of 4 raised to the t power. Alright, so that means in order to get rid of the cube root, we have to raise this side and this side to the third power. So that's going to get rid of that power of 3. So once I do that, then I'm left with whatever this is equal to. Raised to the 3 equals, and that will just, the root and that will cancel out, is equal to 4 to the t power. Now, we have t as in a power. We have to do a couple of things to rewrite that, but let me see if I can rewrite this in terms of power of base, same base, like we saw some exponential problems before I show you a different method, because we hadn't got to logs yet, and I don't know that that would help. So let me see what this actually is in here. So if I do second, quick, I'm going to see what this is equal to 15,968 divided by 998. That gives me 16. Okay, great. So this is what I'm looking at. 16 to the third is equal to 4 to the t. I can rewrite 16 as a base of 4. This is 4 squared raised to the third equals 4t. And then 2 times 3 will give you 6. So you have 4 to the 6th power is equal to 4 to the t power. And from there, when the bases are the same, you can just solve for t and you get t equals 6. So you can solve it by hand. It takes a few steps and some thinking, and you got to recall properties of exponents that we used prior sections. So anyway, this case is 6, much faster if you have the technology to just plug it in.